Right. When you look at this kite, you first establish the area formula as being 1/2 the product of the diameters, so d1 times d2. And so we need to know what those are. Well, we know that one of the diagonals is bisected, right? The diagonal that connects the two unequal sides. So we know that these two lengths are going to have to be the same. So I'll call that x. And then the other diagonal is the sum of these two pieces that are cut off here. So we're going to wind up finding each piece individually. So I'm going to first take a look at one of the right triangles created in this upper symmetric unit of the kite. The diagonals intersect at a right angle, so we do have a right triangle here. So this triangle in red, we know a 20-degree angle. We have this opposite side, some unknown x. I'll call this adjacent side y, and then we have a hypotenuse of 10. Well, with respect to this angle, x is opposite, and 10 is the hypotenuse. So which trig ratio relates opposite and hypotenuse? The sine, right? So we can set up the ratio sine of 20 is equal to the opposite side x over the hypotenuse 10. If we multiply both sides by 10, we get our length x. So here is our measure for x. X is 10 times the sine of 20. Okay, now, if you're looking at this, since this x is the same thing, we can actually fill in the first part of our area formula. The diagonal one is simply going to be 2 times 10 times the sine of 20 degrees. Okay, so there is our d1. We can actually plug that whole value in because we know that those two pieces are equal. Y is a little different. Okay, in order for us to solve for y here, we can use the same right triangle. Okay, this time, though, with respect to this angle of 20 degrees, y is adjacent to it. Our known value of 10 is the hypotenuse. So what trig ratio relates adjacent and hypotenuse? This time, cosine. Okay, so we know that the cosine, we can set up the ratio cosine of 20 degrees has to equal the adjacent side over the hypotenuse. And once again, if we isolate our y, multiply both sides by 10, we get our length for y. So when we look at this, we know that this whole diagonal is simply going to be y plus, and I'll call this z. So if I add y here, 10 times the cosine of 20 degrees, and we need to add just the length z to this to get the remainder of our diagonal 2. Okay, so let's take a look at z. In order for us to solve z, we're going to have to use this other right triangle form on that upper symmetric unit of the kite. And so here we have an angle of 50 degrees. We do know this opposite side now is 10 times the sine of 20. Our unknown is adjacent, so which trig ratio relates the opposite and adjacent? Tangent. So here we get an opportunity to use all three trig ratios that we've talked about in the last chapter. Okay, so the tangent of 50 degrees is equal to the ratio of the side opposite it, which is 10 times the sine of 20 degrees, over the adjacent side, which is z. Okay, so we can solve for z here by doing just a little bit of math. Multiply both sides by z to get it out of the denominator. Then we can isolate z by dividing both sides by the tan of 50. So there is our value, our length z. So if we add this, so 10 times the sine of 20 degrees all over the tan of 50, okay, we'll have our solution. Okay, so now it's just a matter of calculating this. It's a complex calculation, so you do need to use your calculator for it. If we enter this 0.5 times 2 times 10 times the sine of 20 degrees, okay, and then we're going to multiply that by this whole quantity, 10 times the cosine of 20, plus 10 times the sine of 20, divided by the tan of 50, and close that off. Okay, and once we do this, I did use 0.5, so I've already entered it as a decimal. My answer should be displayed as a decimal, and I get 41.95 approximately for my area. It is a two-dimensional measurement, so it's square units for the unknown units.